Hi everybody. Can you hear me? Does it work? Yeah? Okay, great. So thank you, Andrea, for the nice introduction. My name is Dina, and I'm going to talk to you today about ETW and all the cool things you can do with it. So ETW is a monitoring framework. So we're going to start with discussing a little about the challenges that face us with traditional profiling and monitoring tools. And then we're going to embark on a very long, or rather multiple short demos, through which I will try to show you some, but definitely not all of the things that you can do with ETW and the tools that are available to you for this purpose. So let's begin. As I said, first I want to discuss a little the challenges that we face. So there's a lot of tools out there for both profiling and debugging our applications, but I think that the biggest problem that we face with them is that they're invasive, usually. Most of them require recompilation or at the very least restarting your application because they actually inject their code inside your application in order to be able to count and measure all of the stuff that you're interested in. So, for example, if you're familiar with the Intel Parallel Studio, I think that the lowest level of profiling available there causes an overhead of 2 to 20 times, by a factor of 2 to 20. That's a lot. So if you have, say, a 1-minute scenario that you need to profile, I guess you could wait 5, 10, maybe even 20 minutes to get the results of the profiling. But what if you have an application where you need to wait like 5 minutes until you get to the point that you need to profile? Or maybe you just don't know exactly when the problem happens. You just can't afford doing that. A factor of 2 to 20 is obviously not acceptable. The next problem that we have with these tools is that they're more suited for development environments. Because even if you can live with the overhead, even if you don't mind waiting, at the very least you need to restart your application. And that's obviously not always possible in production. What if you need to profile the stock exchange? Or maybe you're developing a military or a healthcare system. You can't always restart the application as many times as you want, like you can on your development environment. And the last problem we might face is something that people don't usually think about, and that's licensing. Because most of these tools, at least the ones that I know, they don't allow the redistribution to your clients. So even though you can debug or profile your application in your development environment, you can't use the same tool at your client's machine. Even if they do allow redistribution, you usually get one license, and it's usually pretty pricey. And what if you need to monitor dozens, hundreds, or even thousands of production servers? Just not going to pass. So you need to find a better solution for monitoring your production environments. And luckily for us, that's what we're here for. There's a solution. It's called ETW, Event Tracing for Windows. ETW is a structured logging framework which supports hundreds of thousands of log messages per second, and it comes incorporated into Windows. And the best thing about it is it doesn't have, well, obviously, any of the disadvantages that we mentioned just now. So, for example, it doesn't require recompiling your code. And its overhead is very small. So, for example, excuse me, for example, if it's turned off, the cost is a few cycles per log message, which is like really nothing. And if you do turn on the logging, then of course the overhead depends on the amount of data that you want to emit. So that kind of depends on you. And of course, I forgot to say, it can be turned on and off on demand while your application is running. So you don't have to recompile your application, and you don't have to start it again in order to get the monitoring. And It's incorporated into Windows, so it's free for you as a Windows user and developer, and it's basically everywhere inside the system. You can get events from the kernel, you can get events from user mode stuff. It's all over the .NET framework. It's in drivers, in servers, in services, in third-party components. In fact, I recently found out that even Chrome can emit ETW events upon request, so that's pretty cool. So, although in order to understand the rest of the talk, we don't have to go into much detail, I do want to spend a few minutes to go over the architecture of ETW, because it never hurts to know a little bit about the tool that you're working with. So ETW has three main components. These are providers, controllers, and consumers. And their names are pretty indicative. The providers, these are the objects inside the system use the data. They emit the log messages that we're going to monitor. The controllers, they control the entire thing. You can use them to start, stop, and configure your logging sessions. And the consumers, well, they consume. They're the ones that are responsible for either logging the data into your hard drive to files or analyzing the data in real time. And we're going to see examples of both these things. Now, the relationship between these three components is not very surprising. What happens is that the logging is arranged in event sessions. And these event sessions are controlled by the controllers. They start, stop, configure them, whatever. And these event sessions, they have multiple producers which emit their events into buffer pools, into memory buffer pools inside the session. That's, of course, for performance reasons. And then you can have multiple consumers which consume these events from these buffer pools, either, again, writing them to files or just analyzing in real time. Now, note that because of these buffer pools, some events might be dropped if you don't write them to the disk fast enough or your analysis process is not fast enough. So conveniently for us, the event session actually holds the number of dropped events, and next time you decide to profile a similar scenario, you can just increase the size of the memory buffer. Everything is highly configurable there. So this is a screenshot of some of the providers I have on my machine. The font is small, and it's totally okay if you can't read it. That's not the point. The point is that there's a lot of them. In fact, on my machine, I counted slightly over 1,000 providers, and each of them can be configured by different keywords and different verbosity levels. So there's quite a lot of options for you out there. And again, it's literally everywhere. So now that we know a little bit about what ETW is and how it works, let's look at what we can do with it. So the most common thing you can do with ETW is analyze your application CPU-wise. It turns out that ETW can save call stacks for each of the events that it emits, or almost each of the events that it emits. And so what you can get from that is that by simply sampling the CPU and getting the instruction pointers for where it happens, you can get a pretty good idea of where your application is spent in time. So in this slide, we can see a screenshot of an application called Purview. We are going to talk about it in more detail later on. For now, just remember that it's an application that allows you to watch, to open and analyze ETW log files. And what we can see here is we can see a list of functions and how long they took. And in this specific case, we have a recording of an application which spent quite a lot of time in calculating primes. Now you can see two functions here. One is called managed processor is prime, and the other one is native processor is prime. And the reason they're both here is that I wanted to show you that ETW actually works for both managed and native code inside your application. And that's very important because obviously your application is not always 100% managed. Well, it's never 100% managed, but sometimes you're also interested in the native parts, and you can get information about them as well here. Another thing you can get from ETW is information about garbage collection. This is also a screenshot from Purview, and you can see a list here which summarizes all of the garbage collections which happened inside your application. So you can see how long the GC took, how much memory was freed, how much was promoted, and so on. But not only that, you can actually get all the call stacks of where GC happened. So, for example, again, a screenshot from Purview. I guess you figured by now that I really like Purview. So in this screenshot, you can see that GC was called 20 times from GC add memory pressure. And that probably means that our application is using a lot of native memory and managed memory. And you can also see that GC was called 13 times from allocating objects. So that means that the CLR actually felt memory pressure and decided to do some collection before it can create more objects. Now, I don't know if you were amazed this far, but not only that, but you can actually get call stacks of where specific objects were allocated, and I find that pretty amazing. So again, a screenshot from Purview. You can see all the call stacks where strings were allocated. And in this specific case, it's a screenshot of an application, a certain WPF application, which managed to allocate 1.5 gigs of strings in some indexing function. Maybe it's okay, maybe not. Oh, I didn't develop that application. But as a developer, if I did develop this application, this can be very useful information for me when I'm trying to diagnose or analyze my performance of the memory allocation in the application. Just another small example of things you can do. You can diagnose what happens when your process starts up. So, for example, you can see a list of all the images that were loaded on startup and their sizes. And you can get, again, a summary table of all the JIT that happens in your application. You can see how long it took and which functions they were. Again, might be useful information. You can get information about file I/O, which files are accessed, what permissions, and so on, their sizes. And if we go back to CPU, I do need to mention here that all of the data about CPU is emitted per core. And that means that you can use these ETW events to analyze your concurrency efficiency. So what we have here is a screenshot of, this time it's not Purview, it's a screenshot of the Visual Studio concurrency visualizer. And in this diagram, green means that a core is actually doing work, and red means that it's blocked. So what we see in this image is that we have a poor locking model, probably, because even though we have 4 cores, de facto, only a single one is doing work at each moment in time, and that's obviously a shame. Here's another image we can get from this information about the different cores. This time we see that we probably don't have a locking problem because the core usage is much better, but we probably have a poor workload distribution because the first core worked twice as long as the last core, and obviously we could have done better. So the raw data for the Visual Studio concurrency visualizer, it comes from ETW, and that's how you can get all this information. Now, okay, that was an overview. Let's go into more detail into some of the scenarios. So back to our favorite Purview. Purview is a free tool. It's available for you for download from the Microsoft Download Center. It's still being released from time to time, so it's relatively up to date. And although not very visually appealing, like you already saw, it provides a very good functional UI for controlling, configuring your collection sessions, and later analyzing the data. It comes with a lot of built-in views, statistical views, and raw views of all of the events. And in fact, it also gives, you can can also write plugins for Purview, but I've never done that, so please don't ask me about it, but it's possible. So let's look at a little something. We don't have much time, although I have recorded all of the demos. We're just going to stick it with screenshots, because I think it will be better for us. We're going to use Purview in order to profile the Visual Studio startup process. So what I'm going to be interested in is opening Visual Studio, not a file, not a solution, not a project, just simply opening Visual Studio and waiting until, it kind of responds to what you're doing. So first, I will define what it is that I want to collect. So that's the collection. Oh, wow, OK. That's the collection window in Purview. And you can see that there are a lot of options here which you can configure. You can configure the buffer size and excuse me. You can configure the producers, the providers that you're interested in. So for example, we're kernel-based, it's pretty basic. It gives you all the information about processes and threads and stuff like that. And of course, we're interested in CPU samples because I am going to be interested in profiling the CPU. I decided to look at file I/O. I want to see which files are being accessed during the Visual Studio boot. And since I know that I have managed parts in the application, I also collect .NET. So again, I'm not going to show it here, but I started collecting information. I started Visual Studio. I waited till it, got responding, and I stopped collection. I got a file. And I opened this file in Purview, and I looked at the call tree, at all the call stacks that it has collected. And what I can see here in the call tree view, it's grouped by threads, and I have the startup, the main thread here, and I see that the entire boot process that I collected was 17 seconds, 11 of which were on the main thread. Okay, we can continue drilling down inside the call stacks, way down below, until we come to a familiar function, and we see that JetBrains used up 5 seconds out of my 11 seconds on the main thread. Now, by the way, I love ReSharper, okay? Just don't get me wrong. I really do. But that's 5 out of 11, and the main point here is that I didn't open a solution, like I didn't have to do anything. I just opened up Visual Studio, no file, no solution, no anything. So I don't know, maybe someone can help me. Since we're talking about startup times, obviously JIT information is also important. So you probably remember that's the image we saw in the beginning of the slides. That's how I got this screenshot. And that's the main thread here, okay? Now, these JIT times, they don't look maybe a lot to you, but they add up, and in fact, I summed up, you don't see all the table here, but I summed it up, and it's like 5 seconds. So it's like 5 seconds of JIT on the main thread. So again, I mean, I don't know, like maybe it couldn't be done any other way, but as a developer, I think it's very good information that I get, because I see this and, I can start thinking, well, maybe I can find a way to do stuff in, some other way. So very good information here. Okay. So far, we used a tool in order to record. It was somewhat manual, right? Like we knew we had a problem, we went to the machine, we turned on some tool, we started collecting, analyzing, and so on. But it turns out that it's possible to automate this process. There's a library, .NET library, called Trace Event. It's available in NuGet. And what it does is that it provides a programmatic API for controlling, recording, defining, configuring these trace event sessions. And you can use this API to record your environment, both from inside your process or from outside your process. It doesn't really matter because the collection is done machine-wide anyway, so you can choose what you want to do. And so, for example, one thing you could do with it is profile your own application for using too much CPU. For example, I could detect using, say, performance counters that my own application is using too much CPU. If that happens, I can start an event session right away and start recording for a while, for a minute, 2 minutes, I don't know, until the CPU goes back down, whatever you think is good for you. And then later I can just take this data, send it back to the development environment, and analyze why was the application taking too much CPU at the clients. The clients don't even have to know that you did that. They would get improved versions all the time, and it's magic. So I did that. I wrote, oh, I'm sorry. Let's look at the API first. I apologize. So let's see how it's done. So the thing we're going to need to do is that we're going to need to define the sessions. What happens in ETW is that the kernel and the user mode data, they can't be inside the same session. So we're going to have to define 2 sessions. Okay? One for kernel, one for the rest of the stuff. Next, we're going to define what it is that we want to collect. Like all these checkboxes that we marked in the collect in purview, we're just going to programmatically set them here. So I didn't have enough room in the slides, but the kernel keywords here are the keywords that define what I want to collect in the kernel. So it's process, file, whatever it is that interests us. And then for the user mode session, I asked for the CLR provider because I know that my application is managed, so I need, I need data about CLR. Next, since these sessions are going to stop collecting when they're disposed, I just need to wait for something, before I close them. So, and again, it's up to you what's convenient for you. It could be either a certain amount of time, or it can be that someone manually stopped recording, or it can be that the CPU went down, whatever works for you. Now, the last thing we're going to need, since we have a managed application, we will need data about the JITted methods, because we won't be able to analyze the call stacks without that. So that's actually done also using ETW. Excuse me. It turns out that the JIT saves all of the information about the JITted methods when it compiles them. And by simply turning on the JIT rundown provider, it just starts getting all of this information. And so you can record it. Now, this is a little silly, but the best way I could find to figure out that all of the information has finished emitting was to check that the file where I'm writing this information has stopped growing. This is indeed a little silly, but that's what I found online. If you ever find a better way, please let me know, it would be nice. So anyway, after I have the kernel information, and I have the CLR information, and I have the JIT rundown information, I finally have enough data to aggregate all of the stuff and get my call stacks. So, and here's my demo, finally. So I wrote an application, sorry, which does some heavy-duty calculations. You can see a screenshot here. I'm not going to run it again because it takes time. But basically, I have a button which allows me to start the heavy-duty calculations and to stop them. And I have, in this case, it's manual, but it could be automatic, of course. And I have a button which allows me to start recording an ETW session and to stop it. So I ran this application, and I got the file, and I opened it in Purview. And again, that's the image you already saw before, where we have the isPrime functions. So that's how I got the file from the beginning of the slides. Now the developers can see that in their offices and decide, well, maybe calculating primes is not the most efficient thing in the entire world. Maybe we should do something else. Now, while we're talking about call stacks, I want to show you another application which allows you to view call stacks and, in general, all of the ETW information. So there's another application. It's called Windows Performance Analyzer, WPA. It's also available to you freely from the Microsoft Download Center. It's part of the Windows Performance Toolkit or something like that. And, well, straight away, you can see that it's much more visually appealing, right? It has colors and graphs and stuff like that. And this is the same file opened in WPA. You can see here a list of processes, which is not surprising because, as I mentioned before, collection is done machine-wide. So like all the processes are there anyway. But what's nice about this tool, rather than Purview, is that it gives you this graph, which is very similar to the .trace timeline graph, where you can see the behavior of CPU for your application over time. And you can zoom in and out into different areas. In Purview, you can also select the time frame where you do the analysis, but you don't have this visual view. So if you started recording slightly before the problem and stop recording somewhere after the problem has ceased to exist, it's harder for you to find that time frame that you need to check in order to look at the call stacks. And here it's very easy. You just select an area, zoom in, and the call stacks here get updated. Now, you could open here the call stack view and get very similar view to what we saw in Purview, but I do have to admit that WPA is not the best tool to do that. It's quite slow, and I don't know why, but it could take hours to load symbols. Of course, we need symbols to get call stacks, so I prefer to do that with Purview. However, another very nice feature of WPA is that it has even another way to look at call stacks, and that's flame graphs. I think flame graphs became popular recently. And what they give you is that they give you a hierarchical view of all of the call stacks in your application. And the reason that it's good is that you don't have to start looking at numbers and drilling down tree views and stuff like that. Just by looking visually at the image, you get a very good idea of where most of the stuff is happening. So this area, whoops, this area is much larger than this area. And you can zoom in, of course, because the font is too small and you can't see all the functions. So you can zoom in inside and what a surprise. Again, we see our prime functions, because it's the same data. But here, it's visually very clear what's going on. OK, so what we saw until now is a programmatic, automatic way of collecting data. And then we analyzed it manually in all sorts of third-party tools. But we're talking about monitoring production. We want to do stuff automatically, right? So that's also possible. Again, with excuse me, with that same NuGet library, which I told you about before, a trace event, it also provides an API for analyzing data in real time. And the idea is that it gives you access to type-safe events, which are familiar with the payloads which come with the specific events. So, for example, there's an object called CLR trace event parser, and it gives you events for the GC, for the JIT. There's a kernel trace event parser, which we're going to use in a minute. You can write your own parsers if you know what events you're interested in and you know what payload they have. Or you can always fall back to using the dynamic trace event parser, which just gives you an API to listening to any event and accessing any payload with a dictionary-like API. Obviously, it's not type-safe. You need to know what you're looking at. So let's see an example. What we're going to do now is that we're going to write a little function which allows you monitoring any process which starts on your system. So in this case, I just copied an example from the official documentation from Trace Event. So you'll be able to find it online as well. The first thing we're going to do is that we're going to define a session, because as we know, that's how ETW works. And I'm going to register on the cancel key to stop collecting. Again, because, we need to stop sometime. Now, in this specific case, since we're interested in processes that start on our system, we need to get the data from the kernel provider, specifically with the process keyword, because that's where the information lies. And last, before we start, we're interested, again, in processes starting. So we're going to register on the process start event, which is, again, a type-safe event, which knows about the different properties that come along in the process start event. So it knows it has a process name property, and it knows it has a command line property, and all the rest of the properties that come with it. And lastly, we're going to start the analysis. Now this function is blocking until we call stop for the session. So that's why we had to register here somehow to stop it. Or if we don't want to stop, that's also okay. So, using the knowledge we just learned, it is now obvious to us that we can write our own program which monitors anything we want dynamically without having to restart our applications. Luckily for us, though, someone else has already done that for us. And there's an open source project on GitHub called eTrace, which gives you a command line interface for live monitoring of events. So, again, I'm not going to run it in real time because we're running out of time. So, excuse me. So we'll just see screenshots. So here's the first example. That's pretty much the code that we wrote in the slide before. We want to monitor all the processes that start on the system. So we're running eTrace with the keyword process on the kernel, and we're interested in the event process start. And it even gives us an option to specify which fields of the payload we're interested in. So in this case, we're interested in process ID, image file name, and command line. And when I ran this demo, I started the eTrace, I opened up a few processes on my machine, and I got this nice list. So you can see when processes start. We can also see that Chrome has a ton of processes that start along with it, as you probably already know. Another example is GC. So we can monitor live any GC that happens on our system. Again, eTrace, this time we're interested in CLR, interested in the GC keyword, specifically interested in the event GC start, and this time I'm not going to filter by any specific field in the event, so I'm just going to get a table of all of the information that comes in the event. So they have the process ID, we have the thread ID, we have the time, the reason for the GC, the type, all that stuff. Another thing we can do is a little similar to process monitor from sysinternals. We can monitor any file access on our machine. So again, eTrace, we're interested in kernel. This time we are going to have to define a bunch of keywords. We're interested in the file IO create event. Even though it's called create, that's the event which happens when you access a file. And this is a nice, whoopsie. And this is a nice feature you can see that we can also filter our events in real time by some filtering function. So for example, in this case, what I'm interested in is only DLL file accesses. And again, we can see I opened some processes on my machine, and I got all of these events. I do have to say, though, at this point, that getting call stacks is only available to you after the fact. You can't get call stack information in real time. And that's because analyzing call stacks requires both aggregating all the information that you have, plus it requires symbols. Obviously, without symbols, you can't get the call stack information. Can do is that you can monitor the events themselves in real time, and if you absolutely need the call stack data, you could just collect the data into files, send it over to your development, and analyze it later. Now, this is our last example with eTrace, and it's here for two reasons mostly. The first reason is that I wanted to show you that you can also get events from ASP.NET. So, just good to know. I was saying before that it's available in all .NET components. So, yeah, you have that in ASP.NET. There's ETW in, what's it called? I forgot, the communication framework. So it's really everywhere. And the second reason this screenshot is here is that I wanted to show you that eTrace can also accept recorded files, pre-recorded files as an input. And you can see all of the requests that my server got here. I do have to say, though, that unless you absolutely hate visual UIs, if you already have a recorded file, I would probably go for either PerFew or WPA to analyze it, because it seems just more convenient to me. Alrighty, now the last demo that I want to show you is something which is extra close to my heart, and that's boot performance. It's something I've been working a lot on when I started my current job, and that's how I learned most of what I know about ETW. So, WPA, Windows Performance Analyzer, comes with a complementary tool, WPR, Windows Performance Recorder, and what it gives you is, again, nice visual UI for creating ETW sessions for specific scenarios. So you can control the resources that you want to analyze, and there's, well, not a lot, but there are a few scenarios that are available to you, and one of them is boot. Now, all of the examples that we saw thus far are from recording applications way after the system has already started, right? And you're probably asking yourself, well, how can I do all that for the boot? How can I collect information about the boot process? Well, it's possible using something called autologgers. Hear that? This is it. The idea is that you configure some voodoo in the registry, okay? These GUIDs, which you see here, are actually, I didn't say that, maybe you noticed, each provider, besides its name, it also has a GUID. So you can use the registry to configure all the providers that you're interested in, and all sorts of metadata, such as the file name that you want to record to, the max file size, the size of the buffers, and so on. And then the next time you start your machine, it's just gonna record all of the information into this file. So what happens is that WPR simply provides a nicer UI instead of you defining this voodoo in the registry. Of course, it doesn't give you all the options, so if you need something very specific, you will have to resort going back to the registry. It's not very complicated, really. So I did that, okay? I restarted the machine, and I recorded all of the performance data. And this time, I opened the file not in my favorite purview, but in WPA. And in WPA, there's a very nice predefined view for the case of boot, which shows us something which is called boot phases. You can see, for example, how long it took for the session to initialize, and you can see how long it took to log in. So, for example, if you're logging in over the network and like your connection is slow or whatever, you could see that logon takes a long time. And you can see the time that it took for Explorer to initialize. And then there's something called post-boot. I could define post-boot roughly as the time that it takes the machine to sort of calm down after it started. Because you probably know, like after you start Windows and you see the desktop, it totally doesn't mean that you can start opening whatever you want, right? You have to wait for a while. This is my machine. So that's that time. The post-boot is the time until the Windows actually starts responding to your clicks and opening the applications that you wanted. And we can see that the post-boot here is very, very long. I mean, that's not normal, obviously. So we can use WPA to figure out what happened. One of the things we can see in WPA is, again, another predefined view called transient process view. And the transient, excuse me, the transient process view gives you a graphic display of all the processes that started and stopped during the boot process. So I highlighted here a process called Rabbit Watchdog. I highlighted it because I wrote it, and I know that that's the problem. So, this is not fair. But what you could open is that CPU view, which I showed you before, which shows you a timeline of the processes that are using your CPU. And now it's quite obvious that you can see here there's a process which is using, probably an entire core. Just doesn't stop. And this process is Rabbit Watchdog. Specifically, since this is my own process, I would probably be interested to know what exactly it's doing that's taking up so much time. So, and again, as I said, WPA is not very good for opening call stacks, so I'm going to open it in purview. And I'm going to see that my process spends 99% of its time getting processes on my system. So I guess it deserves its name. But if it wasn't my process, maybe I would consider removing it from the startup list or something like that. So I got information about what's slowing down my boot. So that's it. What are the main takeaways that I want you to have from this talk? Well, first of all, that ETW is an omnipresent component in your system. It's everywhere. And its performance, it's really good. And you can use it to monitor basically anything on your system. So a lot of performance and profiling tools actually use it on their own to do that. And you can do that. I didn't mention that before because it's not the focus on my talk. But you can actually use ETW as a logging framework for your applications. You can emit your own data. And that would allow, I don't know, your DevOps people or whatever to configure in real time dynamically, what kind of information they want to see about your processes if something happens, but nothing is going to happen. I'm sure of it. So that's it. I showed you some, definitely not all, of the things you can do with ETW. In fact, I'm 100% sure there's a ton more stuff that I don't know about. One of the problems with ETW is that it doesn't have concise documentation about all of the providers and keywords and all the stuff that you can do with it. So a lot of times you're going to have to do a lot of trial and error and digging into your systems in order to figure out how to get what you want. that's that. The main thing I want you to remember is that next time, if you have a performance mystery, just ask yourself, can ETW do it? And maybe you will gain new insight about what your application is doing.
Thank you, Dina. Great talk. Now we have time for a few questions. Anyone?
Excuse me.
Можно на русском?
Можно.
Давайте, смелее. Все, вопросик.
Hello, Dina. The question is, what is the performance impact when you turn on the session recording?
Okay, so again, well, here's the thing. With everything that has to do with Windows and like the .NET components, ETW is already there. Okay, so it's just turned off by default, but like you couldn't really measure what the performance is without ETW because like the code is there, right? There's just a tiny if which checks if the provider is turned on or off, so you can't check that. And according to what I read online, that causes an overhead of a few cycles per log message. If you do emit data, it really depends on the size of the stuff that you want to emit. You know, if you emit a single integer, you probably wouldn't have a lot of impact. If you start, I don't know, writing novels, it's gonna cost you more. So it really depends on the data, and you should probably check the impact specifically on your application.
What about application internals? I mean, we saw only processes data like opened DLLs or CPU usage by some file or some process. And is there ability to dive deeper in a particular application? Like function calls and so on?
No, I don't think so. Okay, because it's not like a function tracing framework. It's more again like a logging framework. So if by some way you found out that Windows emits an event when you call file create. Yeah, so you can find that in the logs and you can figure out the name of the event, and well, now you know there's an event when a file is accessed, so you get that. Maybe I'm not familiar, I don't think it exists, a way to say, I want a trace point on this function. It's not a debugger, okay? It's based on pre-existing trace points. You can't create them dynamically inside Windows. So, if that's what you meant.
As I understand, there is ability to build in this functionality in application on
yes,
any
you can definitely emit if you write an application. Then you can, I don't know, like I use Log4net for our logging, but I could just as well use ETW as a logging framework. In fact, I suggested it a few times at work, but my ideas were said to be interesting, but we're not going to spend time on replacing the logging framework. Excuse me. So yeah, so again, it's based on preset points. So they're preset on Windows. You can't, you know, if you find that the function has a trace point, you can use it. But if not, that you can't get it there. And for your own application, just put it wherever you want.